Nicolas Claiser. Nicolas, since 2005, is assistant professor at the of Lorraine at Nancy, France. He works in crystallography, magnetic and resonance and modeling laboratory. Nicolas got his PhD at Nancy in 2003 and then went for a postdoc to the University of Rennes and then returned back to Nancy. His field of expertise is crystallography in general, and in particular charge density investigations, joint refinement, and molecular magnetism. His recent publications are focused on spin-resolved charge density and wave function refinements, determination of local magnetic susceptibility tensors, and in paramagnetic lanthanide crystalline powders from solid-state NMR, chemical shifts, and isotropies. Spin-resolved atomic orbitals modeled, refined from combined charge and spin density analysis, application to yttrium titanate perovskites, synthesis, crystal structure, and phase transition of novel hybrid perovskites. Nicolas co-chaired microsymposia at the IUCR congresses, in particular the last one at Melbourne, Australia, and presented lectures at different microsymposia, for example, the last two European charge density meetings at Padova and Paris. Today, Nicolas will present his lecture entitled Joint Refinement of Diffraction Data, but not only a short story. Nicolas, the screen is yours.
Yeah, good day, everybody. I will thanks Paulina and Christophe to give me the opportunity to present our works in our team in Nancy today to everybody. So as it's right on your screen, it's a short story of joint refinement to the point of view of our work done since more or less 20 years. So this is a common work, so I will start thanking all the people that work on that project, especially Claude Lecomte and Mohamed Souassou, that were from the beginning the heart of that project, but also Dominique Luneau, Béatrice Gillon, Jean-Michel Gillet, and Pierre Becker, that were the very early beginning of that project, and that contribute a lot to developing the results you will discover today. But of course, we need students and good students, and this is what we had with Maxime, Arist, Bolivar, and Léon, and also good PhD students with Yuri, that all together contribute to that huge work that I will present today. And of course, I will thank all the people from the lab, Christian, Benoit, and Gwendal, that already help us to improve and to propose tools for the community. And we also benefit of many other helps coming from all around the world, especially from Japan, from people from Thing 8, but also a contributor from Central Supélec and from LPCT, theoretical laboratory in Nancy that help us to many theoretical calculations. And of course, we have benefit of different financial support, especially from the ANR, Agence nationale de la recherche in France. So why do we want to study to define a charge density or electron density model? Because, of course, doing a high resolution X-ray diffraction, that gives you the best representation you can obtain from a crystal. Based on the model you can obtain from that, you can apply a topological analysis based on the border analysis that give you many information on the interatomic interactions. You can also do calculations to define what are the electrostatic properties of your system. It's very interesting if you speak about the protein active site, but it can also be applied to many different systems. And in our case, we particularly focus on the magnetic properties. And for that, we decided to propose what we call joint refinement. It means combining X-ray, neutron, and polarized neutron diffraction experiment together in the same model. And the aim was, among that, to be able to propose a very precise model that can be directly compared to the more precise theoretical calculations, because we imagine that theory and experiment must go together. So, just by curiosity, I asked to a well-known guy, which is ChatGPT, what he knows about joint refinement. And the answer I received was not so bad, because he knows that it's concerned mainly X-ray diffraction, neutron diffraction, but also electron diffraction, which is in fact very completely true. And he also points out the interest of doing joint refinement. He points out first that combining experiments give you a more robust model, especially if you speak about the structure. It has also the interesting of, by combining experiment, to have a more complete description of the system you are interested in. And of course, it helps to obtain a more precise description of the system. But he points also out that you can, if you want to have a joint refinement, to use constraint and restraint, because it's not so easy to combine different experiments together. So, good point. What about the real history of joint refinement? If you are looking back in time, you will discover that since many years, people are interested in combining experiment. It could be X-ray and neutrons, could be mainly for the structure refinement. And it's very interesting to see that, of course, good ideas came from sometimes from very long times. Just the difference is we are now able, because we have more precise experiments and we have also very powerful computer, we are now able to be in capacity to really apply that ideas. So I will particularly point out the works made by Pierre Becker and Philippe Coppens, because in that works, they claim that it's possible to represent the model by decoupling the population of spin up and spin down. And they also predict that that will induce a difference in expansion from the both spin up and spin down distribution from 1 or 2%. This is something very interesting. I will come back on that point later. So, well, our idea, it's very, huge project, was to be able to combine a lot of different experiments in the same model. Of course, we talk about neutron diffraction, X-ray diffraction, but also polarized neutron diffraction. But in our idea, we also imagine that it could be possible to combine together compound scattering and magnetic compound scattering to have a very complete overview of the system. And for that, the tool that can be applied for introducing all the elements together was a one electron reduced matrix. And I will not describe too much that matrix, because Jean-Michel gave a very detailed lecture previously on that subject, and I will recommend to look again at presentation. What I'm focusing in is the way you have to conduct that joint refinement. So, if you consider any isolated experiment, for example, X-ray diffraction, you will extract from X-ray diffraction structure factors. That will be the way for you to model a charge or electron density. And for that, you will define a chi-square. You will do exactly the same for polarized neutron diffraction. That gives you the magnetic structure factors. That helps you to model the spin density with another chi-square. And again, you can do that for many, many different experiments. But the question at the end is, okay, what could be the common model for all the experiments? And moreover, what is the function to consider to refine that model? I mean, and also the question of what are the parameters I have to consider to refine that model. So many interesting aspects that are not so easy to to answer. And what you have to consider is if you speak again only about X-ray and polarized neutron or neutron diffraction experiments, it's concerns the diagonal part of the density matrix, which is of course the more simple case, because in that case you can only consider that changing the sign from X-ray to polarized neutron, you can use the same model, and that model can be maybe derived from the Hansen and Coppens model. I will rapidly remember you with the Hansen and Coppens model. It describes the electron density as a sum of three different terms: the core, which is frozen in our case, a spherical expansion model for the valence density, and an aspherical model, which is able to reproduce all the different aspects of the atoms in the different systems. So our idea was just to split, this is what we call the spin split model, to split the spherical valence, which is the second terms, and the aspherical valence term in two contributions, one for the spin up, another one for the spin down. And this is what we proposed 10 years before. But again, as ChatGPT told you, you have to introduce constraints if you want to do a joint refinement. Of course, electron neutrality is very evident, but you also have consideration for the magnetic information you have for the system. For example, for the saturate value for the total magnetic moment, which is another constraint. I will not develop too much, but you have different kind of supplementary constraints you have to introduce in your model to be able to refine it. So let me then describe the first application of that model that was applied to a copper-2 complex. The copper-2 complex was proposed by Dominique Luneau. As you see on the picture, it's made of two copper atoms interacting through an azido bridge, which is made of three nitrogen atoms. And what is interesting in that system is you observe from the magnetic behavior that the apparition of ferromagnetic interaction at very low temperature. So the idea of people was to try to understand what is the mechanism leading to the interaction, to the ferromagnetic interaction between the two copper atoms. They made different kind of experiments, X-ray diffraction, neutron diffraction, and polarized neutron diffraction. It means that you have all what you need to carry out a joint refinement. And this is what we did. We take all the different informations coming from the three kind of experiments together. Of course, since it was not the idea at the beginning of the project, the temperature are different, but this is something we can handle with. And we did the first refinement combining those three different experiments. And here you can see the results of, on the left, for each dataset treated separately, and on the right, from the agreement factors obtained after the joint refinement. And you see that you have something which is very good if you consider, if you compare each experiment separately, because for the joint refinement, you have agreement factors that are very close to the one you can obtain for isolated treatment of each dataset, which means that we have something which is very good at the end and very close to previous works. Of course, we more precisely look what we obtained, and especially the charge density distribution around the atoms. Of course, in that case, the X-ray diffraction give you many more information on the system than any other experiment. So it means that the final model should be not really affected by the way that you are carry out joint refinement. And if you observed the distribution of the charge density around the copper atom, you see that the maps are very close if you compare the one obtained from the X-ray diffraction experiments only to the one that is obtained after a joint refinement. And again, the argument factor are very, very close. It's clearly different if you consider now the spin distribution, because of course, one of the main advantages of the joint refinement is that you can introduce many more parameters in the model, because you don't consider only one experiment, but a lot of information coming from 3 different experiments. And if you look the number given there, you see that the number of parameters in case of joint refinement that have been applied to the modelization of the spin density is more than twice the one you have for spin-only refinement. And of course, you see that the spin distribution obtained for the copper atom is clearly more precise after joint refinement. So what we have been able to see also is the fact that if you now looking for the expansion of the spin up and the spin down density, you observe that the kappa values are different, and the difference is around 4%. And this is very interesting, because if you are looking back what was predicted by Becker and Coppens, they imagined that it was possible to see such a difference, but in that case, they predict only 1 or 2%. So anyway, it's very interesting to see that experimentally we have been able to confirm that it's possible to see the difference in the expansion of spin down and spin up. So we already ask people to do theoretical calculation to compare what we obtain from our experimental approach to that theoretical calculation. And this is what has been done by Jean-Michel Gillet. And you see, comparing the both model, that they are already very close, because spin density predicted by Jean-Michel using DFT calculation is very similar to the one we obtained using the joint refinement. So at the end, we have been forced a very good resolution of the spin density distribution around the copper atoms. But what is already interesting is, in fact, you have access to the spin down and the spin up and spin down distribution separately, and you can plot them. So you can have maps showing only spin up on the left, or only spin down on the right, and you see that the distribution are not the same. And this is okay. This is what you can see there, because the spin up is completely spherical, but the spin down is not spherical. You see that you have a DXY shape, and if you compare that distribution to the same calculation made by Jean-Michel, you observe that they are completely comparable. You have very similar distribution of spin up and spin down around the copper atoms. You can also project the model you have for the spin distribution around the copper atoms on orbitals, I mean the d orbitals of your copper atoms, and obtain distribution of spin up and spin down that indicates that you have something which is very homogeneous for the spin up, but it's not the case for the spin down, with the dxy minus y square orbital and the dxy orbitals that are clearly not homogeneous in terms of spin down population. And then gives you a kind of a representation of what is the spin distribution on the copper atom in the system. So to conclude on that first part, it will be the demonstration that it's possible to combine different kind of experiments to be able to refine experimentally spin up and spin down population on that system. For that, we developed a specific program. We call it MOLI-NX for the refinement of X-ray unpolarized and polarized neutron diffraction data. And of course, MOLI-NX is now included in the MoPro software package distributed in our lab. Okay, so another example of joint refinement applied to in that case a pure organic radical, a nitroline hydroxide radical. So for that, we consider the work done before by Kaneshi and co-workers. There have been studied radicals presenting a specific organization made of layers. You have, in fact, radicals that are associated in dimers. Okay, yeah, like as you can see there. And what they predict to explain the fact that you observe the ferromagnetic ordering at very low temperature for that kind of radical, they imagine that the transition must be driven by the interplane interaction through the contact between the sulfur and the methyl carbon atoms of the humidizer ring. It means between that part of the molecule and that terminal part on the other side from two interacting radicals. And this is something that have already been explored by previous works, because colleagues have been made a neutron diffraction experiment and also polarized neutron diffraction experiment on that radical system. And they have been able to, using first maximum entropy method, to obtain the distribution of the spin density in that radical. And as expected, you obtain major contribution of the spin distribution coming from nitrogen and oxygen of the nitroxide function. But what was interesting in that case is if you look at the projection on the plane perpendicular to that function nitroxide, you observed that the 2pz shape is not exactly the same from both parts of the system. It means you have a kind of asymmetry. And this is something you can observe more precisely if you use a model. And this is what they did in the same work, using a wave function type refinement. They've been able to have a more precise representation of the spin density in that system. And it was clear at that point that you have an asymmetry considering the spin distribution from the two arms of the nitroxide function. And what they also be able to point out is the presence of a positive spin population on the terminal carbon atoms close to the sulfur atoms, which was completely in line with the prediction that that part of the molecule is involved in the intermolecular contact, explaining the very low magnetic behavior. Colleagues from the labs have studied that materials using X-ray diffraction, and they have realized experimental charge density model. They have been pointing out the fact that it's possible to, using a topological approach, to point out that specific interaction between the two radicals. And in practice, it's possible to have numbers for all the hydrogen bonds present considering a dimer. It means that you are able to observe the intramolecular hydrogen bonds that are in blue. That's a direct interaction between one part of the radical and the nitrogen nitroxide function, but also contribution in red in my table coming from the inter-radical interactions. And again, you see that both O1 and O2 are involved in that interaction. So, okay, what is the conclusion of that is you observe if you do spin only analysis that the spin distribution is not identical for the two arms of the function. If you charge density analysis, you observe that again, you can see that on that map, that especially the lone pairs of the oxygen atoms are not identical. So it means you have a dissymmetry that comes maybe from, this is what we imagine, that came from the different hydrogen bonds that are involved, that are present for O1 and O2 in that system. So our idea was to combine X-ray diffraction and polarized neutron diffraction experiment together in a joint refinement to have a more precise distribution of the spin density in the system, and also to compare that to a very precise theoretical calculation. And that theoretical calculation are DFT calculation and KSSF calculation. Okay, so let me just describe what we obtained from that. We obtained very good agreement factors for both X-ray and polarized neutron refinements. And what is interesting, if you compare what are the spin populations obtained for polarized neutron diffraction only or for joint refinement, they are close, but they are not identical. You observe slight differences. Okay. Now, if you just want to have an idea of the quality of the joint refinement, you see the residual maps obtained for the total electron density, and they are very clean. And the model you obtain by your experiment is very close to the one predicted by calculations. So again, it means that everything is okay. But if you now compare what happened specifically on the nitrogen hydroxide function, you observe that again, you have a dissymmetry for the experimental part, which is not reproduced in the calculation made by DFT calculation. So it means that that is maybe a limitation of that kind of calculation, that are not sensitive enough to that very, very tiny aspects of the interaction in that kind of materials. So we also have the same conclusion if you look the spin population you have on that kind of functions. So our idea was to not use DFT calculation, but to use KSSF calculation, because in principle, it should be more sensitive to that very tiny effect. And that works, that calculation has been made in collaboration with Alessandro Genoni and Marco Marazzi, at that time at the LPCT at Nancy. And the results were very interesting. Of course, for that calculation, we consider the two interacting radicals. We call that a dimer. And you observe here the result of the Millikan spin population obtained from that kind of calculation compared to the exponential value. And you see that if you just first look the exponential value, you have a dissymmetry if you compare the summation of the spin density on one arm compared to the second arm. And this is something which is clearly appearing in the KSSF calculation, but is not so clear, I will say maybe not at all, in the DFT calculation. So what can we conclude from that is in such a kind of system for which the effects are very tiny, you have very, very small interactions that are very appearing at very low temperature, it's really important to have a convergence between your calculation and your experiment. So if this is not the case, you have to check all the experimental parts, all the theoretical parts, to be sure that at the end you will have a convergence. Okay, let me then move to the last example, which is concerning inorganic material, yttrium titanium oxide perovskite. So it's based on the ideal perovskite structure AbO3, you can see on the left. But in that case, you have significant deformation with angles between the titanium octahedra that are around 140 degrees. The space group of that yttrium titanium oxide is PNMR, and you observed fermatic ordering at very low temperature, below 29 K, with an anti-fermatic orbital ordering. This orbital ordering has been studied. I will describe it later, but I will first focus on the specific geometry of the titanium octahedra, for which you have an elongated distance for O2 prime, which corresponds to our z-axis there, compared to the two other equatorial distances. And so, as I told you, you are considering the spin distribution around the titanium atom. It's possible to obtain a good representation of the spin distribution using maximum entropy method, again, based on polarized neutron diffraction experiments. And this is what you did, and this is the result presented on the right part of my window. You see the shape of that distribution, and it's completely in line with what has been described previously by Akimetsuko and co-worker, that indicated that the spin distribution have been satisfactorily explained by the linear combination of the wave function Z, Y, and Zx in terms of orbital ordering scheme. But in that case, they force the system to be modeled by that kind of combination. In our idea, it was better to just refine jointly X-ray and polarized neutron diffraction experiment together, and at the end, consider if the spin distribution we obtain around the titanium atom will have the same shape than the one observed by our colleague in Japan. So we made a specific X-ray diffraction experiment in Sprigate, Japan, very good condition because it was possible to reach very low temperature, and we have a very short wavelength, which is recommended if you consider the fact that you have yttrium and titanium in your compounds. So we have very good quality dataset for that joint refinement. And in that occasion, we developed what we call the atomic orbital model. In that case, you describe the electron density as a sum of two different terms, which is atomic centered terms, the first one, and the second one that introduces the bicentric contributions. The model is based on atomic orbitals. You see here the definition of them, that are rely on basis functions that I made of the product of radial function and spherical harmonics. And we decided to apply a normalization constant, which is the one I just described there. So this is a model we developed for the study of that materials. But of course, again, you have to introduce constraints to be able to refine such a model. Constraint for the electron neutrality, constraint for the spin also, and again the constraint on the orthogonalizations of the different functions you will be used to describe the systems. What is interesting if you use such a model is you reduce a lot the number of parameters required for refinement. You see, compared to a multipolar refinement, you divide it by 3 the number of parameters you need to consider for that modelization. So what is the result of such an approach in that case? I will focus on titanium atom because it's the one which is possessing non-paired electrons. And you observed in that case that the spin population is mainly carried on titanium by 2 orbitals. The first one is the pure 4s orbital, and the second one is a combination of the dzx and dzy orbital. And what is interesting to see is if you compare the orbital model to the multipolar model, you see that the maps are very close from both models, as you can see here on the maps plotted with contours of 0.05 electron per action cube, because it's something which again shows that the major contribution came from the dx. So it's observed from the dxz and the dyz planes. So the difference here is, in our case, we don't make any a priori on the spin distribution in the model. We just completely describe the charge and spin density of the system, obtaining a very precise description of the system using multipolar or atomic orbital models. And this is, at the end, completely in line with that work done by a Japanese colleague before, but without any a priori, and with a complete description of the system. So it's time, or more or less time, to conclude, because before conclusion, I will just speak a little bit about a very interesting story. We have a collaboration for some years now with Siam Kamal from Cairo University. She's producing a lot of different kind of hybrid perovskites, and we are particularly interesting in that because it could be a good way to have particularly interesting magnetic interaction between two magnetic centers if you are able to play with the nature of the metal and the distance between the different metals. So the example I want to focus on today is made of two manganese octahedra. As you see on the picture, you have an equatorial plane from that octahedra, which is made by chlorine atoms, and you have an apical direction, which is occupied by water molecules. So each octahedra share two chlorine atoms with another manganese atoms. This is the distribution you have of your system. What is interesting in that is you have for the organic part, you have propane diammonium molecules and also isolated chlorine atoms that ensure the electroneutrality of the system. So in that measurements, we use low temperature data collection, and you see that the space group is P-1, for triclinic 1. Okay, we just we made a complete description of the system. Of course, you observe that if you consider the bond length in the octahedra and the angles, you have very small distortion of the octahedra with shorter bond length if you consider the apical direction for which you have water molecule in coordinations. What is interesting in the system is if you make a DSC experiment, you see that you have different results depending if it's the first heating or its second or third heating. For the first heating, you have in black or in green in my graph, you see that you have very huge endothermic peak appearing around 100 Celsius degree. But if you go down in temperature after the first heating and want to warm it again, you see that the blue curve didn't indicate such a behavior. So it means you have a position which is not reversible in your system. And it happens between 360K and 355K with some events at higher temperature. So we realize the powder diffraction experiments on that temperature range. And this is the results of the summation of the different powder diffraction experiments. You see that a very huge transition appear close to 100 Celsius degree, and you have smaller events at higher temperature. So these are the spectra of the different temperature domain. And again, you see that the larger differences are observed between the 30 Celsius degree graph and the 150 Celsius degree, which is corresponding to the very big endothermic peak described previously. If you look what happens if you now check for the magnetic behavior of that system, you see that, again, the magnetic behavior you observed for the first cooling here is completely different to the one you observed for the second or the first cooling. It means, again, to the magnetic point of view, you have very different behavior after the first heating. And this is something which is, again, the sign of a transition happening at the first heating. If you want to model the magnetization obtained at 2 Kelvin, it's very easy to model it with two interacting manganese 2 plus atoms with a spin 5.5, but it's not possible to explain what happens after the first heating because the signal is completely different, as you can see on the red curve there. So we try to obtain the structure after the first heating, and this is the result of the attempt we made. You have a huge contribution from powder diffraction and small contribution from the surviving single crystal in your sample. So it's very difficult to deal with that. So we ask our colleague for powder diffraction to give us a possible unit cell, and this is what he proposed, which is very different to the one we have initially because it's completely different parameters and different system. But with that, it has been possible to treat the peak we have been extracting from the data sets after the first heating, and we have obtained such kind of model, which is, of course, very surprising because completely different to the initial structure, which is plotting there. So in that case, we have three different manganese interacting with only chlorine atoms. So it was surprising, but the advantage of that high temperature structure is it helped people studying magnetics to fit what happened after the first heating, which is completely in line with the measurements they made. So it means that it's probably the good structure, but of course you need to confirm that. And for that, okay, as I say, help you to fit the magnetization using three different manganese interactions. And to confirm that it is a good structure, we ask people, colleagues from Grenoble, Dominique Housset, Stéphanie Kolikidjian, and Holger Klein, to make measurements on very, very small single crystals to extract the structure of the materials after the first heating. So, as you know, electron diffraction is something which is very destroying your samples, and they need two different crystals to be able to collect enough information for what we are interested in. They, at the end, obtain 12 data sets that are being merged together. And the final metadata give you very good completeness for very good experimental resolution, which is very, very high for such kind of experiments. Here you can see more details about the data collection. And what is interesting is using electron diffraction, you're able to have in that case, to have a very, very precise structure because they've been able to precisely define where are the propan diammonium molecules in the system, but they also be able to identify from one side that you have a disorder for such kind of molecule, which is completely not possible for mixed-ray diffraction, because this is what you obtain. It's in line, but really, really more precise for electron diffraction.
Nicolas,
just
Nicolas, I'm sorry, let me interrupt you. We stopped seeing your screen.
Before concluding, I will say that it's not the end of the story, because if you wait a little bit, you see that after some months, the magnetic signal came back to the one that you are initially measuring on the system. And if you take one of the crystal corresponding to the later magnetic measurement, you see that the structure you obtain is again the same as the one you have initially. So it means that the water molecules come back in the system, and you again have now manganese dimer together in the crystal. So to conclude, finally, what I want you to remind is a joint refinement gives you a very precise description of your system, and in our case, especially from the magnetic point of view, it can be applied on very different kind of materials, as I told you, on complexes, on radicals, on inorganic materials. The problem, I will say, the limitation is you need, of course, to be able to have X-ray diffraction, neutron diffraction, or polarized neutron diffraction experiment on your system, which is not so easy to do. And the good point is it's now possible to use the specific interface for Molienix in the Pro software suite. And we are also interested in integrate new techniques in our model to enrich and to have more precise description of the system. And I will just conclude by indicating where you can find the software, and by thanking all of you for your kind attention.
Thank you very much, Nicolas, for this excellent lecture, which is now open for comments and for questions. Oh, we have already some question from Daniel Kamiński. On slide 19, the extended model doubles the number of parameters. Why is the improvement of R only 1%, if I remember correctly, with such many extra parameters used?
Yeah. In fact, it's true that it's double the number of parameters, but it's true only for magnetic atoms. So it means since the magnetism concerns only few atoms in the system, the number of supplementary parameters is not so huge. In fact, if you speak about the system I just described, for the copper atom, for example, we only split for the copper and for the surrounding atoms. So it's not so much during all the system.
Okay, thank you. And a question from Hans-Bert Birgi. Electron and spin density models are very detailed. Models of atomic motion are very crude, harmonic ADPs. Given this difference, how reliable are small differences in your results? Example, the two NO groups in example 2.
What I mentioned is it's possible to have different thermal parameters for each dataset. So it means, in practical, you are describing the dynamic motion separately from each dataset. So it's not different to what you are doing for a single experiments. So I think the precision we can access should be not different to any charge density refinement you can see regularly in the literature. The question about the small differences you observe in your system is a good question, because as we say, you never know if is the experiment or the theoretical calculations that are right. But what is, I will say, a good point for us is that difference, that dissymmetry, can be obtained if you apply a different kind of calculations. So it means it's not not only an artifact, it's something which is really present. And again, this is something that has been observed in pure polarized neutron diffraction experiment and also in charge density. So I think you have in all that question to double check everything, but at the end, I think you can say that the difference are really present.
There is next question from Julian Hen. How much depend the results on correct standard uncertainties for diffracted intensities?
The main problem in our case is to be sure that the model is not only driven by the X-ray diffraction data. And so I don't know if this is also expected, but this is a reason for what we develop a different weighting scheme that allow you to play with that in order to increase the weight, the relative weight given to, for example, polarized neutron diffraction experiments. And of course, we already check what are the effects of that. But honestly, we never observed that it's clearly difficult to let the spin be really good refined based on that model. I mean, because the split atom, I mean the one for which you double the number of parameters, are only magnetic atoms, and it means that for them the magnetic information is very important, and it makes sense that it's bring you, it's drive you to the convergence of your model.
I missed one point before Julian's question. Coming from Chris, very interesting work. Thanks for the lecture. Are there tutorial X-ray PND data sets available to learn more about performing this refinement?
I don't think so. I don't think so. Yeah, I don't think so. I'm sorry for that, but we don't give tutorials. I mean, you can have tutorials, but you don't have data sets to practice a bit. We provide data sets if you when you organize schools for joint refinements, but they are not available online.
Do I understand situation well? You simply invite people to Nancy to learn a little bit more.
No, we can move. We did school in different in Slovakia, in South Africa, but I mean the main difficulty is to be able to have, for example, polarized neutron diffraction experiment, because you cannot carry that kind of experiment anywhere. This is why we are thinking to have complete experiments that give you access to magnetic information without necessity to have such kind of very difficult experiment.
A question from Jean-Michel concerning this last question. I mean, the last is this one coming from Julian Hen. I believe this is a major concern in the balance between each type of experiments. So how do you balance each type of experiment in your?
Okay, I can show you maybe. I have. In fact we developed a different weighting scheme, and I can show you what are there. So this is what we did for another compound, which is manganese copper bimetallic chain. We developed three different weighting scheme. The one which is just a summation of the chi-square, another one which is a summation of the log, and another one which has been proposed by Michel, which is the summation of the n log of the chi-square. And it's a way to play with the relative weight of each dataset. If you see, I plotted there the relative weight of X-ray compared to polarized neutrons. If you use a very simple one, which is a summation of chi-square, you have a ratio which is clearly favorable a lot to X-rays, which is what you expect because you have significantly more data coming from X-ray diffraction. If you use the n log 1, you will use that balance. And if you use the log 1, it's more or less the same weight, the relative weight, for X-ray and polarized neutron. So playing with a different weighting scheme, you can clearly highlight the role of the polarized neutron diffraction experiments.
Mm-hmm. Thank you very much. Paulina, will this kind of topics be covered by the program of the Richer School or Sagamore?
At Sagamore, I think no, but at Richer School, Nicola is one of the tutors and speakers. So the MOLIX, there will be one of the workshops devoted to MOLIX and to this kind of refinement.
So you see, there is a chance to learn more about this joint refinement. Another question from Hans Bet. Another question on ADPs. Given the different TS of the experiments, how well do the ADPs follow the trend expected for harmonic oscillators?
It depends. It depends on the system.
Difficult.
And, yeah, but it depends on the system. It's not something you have already to take care of that. And I can show you that, for example, for the description of the yttrium titanium oxide, it was not possible to obtain good results if you don't introduce anharmonic thermal parameters.
Mm-hmm.
So in that case, you see that you can see if you have classical treatment of the thermal parameters on the left, you have huge residual maps that are completely improved if you introduce anharmonic thermal parameters.
Mm-hmm.
So I mean, I think the problem, one of the difficulty of the joint refinement is you don't have any receipt. Each sample is different, and I will not be able to tell you that a weighting scheme will work all the time. It just could not introduce some bias. It could be. So you have to check at every stage of the refinement if you are not introducing a bias because you don't taking all the parameters into account.
Okay. Are there any more comments or questions? I do not see any more. So thank you very much, Nicolas, for this excellent lecture and interesting discussion.